Earlier, we have seen the case when vectors are linearly dependent, which is basically a fancier way to say that one of the vectors is a linear combination of the others. And we also have seen the opposite of that, which is what we call linearly independent. Basically, what this means is the vectors that we have, they have nothing to do with each other. I cannot create one of the vectors by using the others. And we have seen that one way that we can use to check whether or not my vectors are linearly independent is to find a solution to this homogeneous system of linear equations. And I need to check that this equation only have one solution, which is the zero vectors. But we have seen something like this earlier. In fact, it was in example 2.3. We knew from then that the solution to this homogeneous system of linear equation is going to be just the zero vector precisely when the rank of the matrix that I get from just putting all these vectors together is n. In other words, if I have n vectors here and I need to check whether or not they are linearly independent, well, I can just put them together into a matrix. So my matrix A is going to be formed by putting a bunch of vectors together. So let's say my matrix A here, this is an m by n matrix. M is the number of rows and n is the number of columns. So n is going to be the number of vectors that I have here. These n vectors are going to be linearly independent. They are going to be linearly independent precisely when the rank of my matrix is equal to n. And n here, this is going to be the number of vectors. Okay, so now that we have this, let's actually speed run through the example that we actually have seen earlier. So for the first example, my n, which is the number of vectors, is 3. If I form my matrix is going to be 1, 0, 2, and then 0, 1, 3 here. This is already in reduced row echelon form. The rank of this guy is 2. So the rank of this matrix is not equal to n. So I can conclude right away that these 3 guys, they are not linearly independent. But for the next one, I have 2 vectors here, so my n is 2. If I form a matrix which is 1, 2, 0, 3, the rank of this guy is going to equal to 2. And because the rank of the matrix is equal to 2, which is the number of vectors, I can conclude then that these 2 guys, they are linearly independent. We actually have seen how to find the rank of this matrix in the example 1.7. And this will apply to the next 2 matrices that we are going to have as well. Now for part C, I have 3 vectors, so my n is 3. If I were to form a matrix here, I'm going to get 1, 3, 1, and then 2, negative 1, 0, and then 7, 0, 1. Well, in the earlier example, we have already found the rank for this guy. Let me just say that the rank of this matrix is going to equal to 2. So because the rank is not equal to n, so I can conclude that these 3 guys, they are not linearly independent. But for the next one, I have 3 vectors. And the rank of the matrix that I get by putting all these vectors together, 1, 2, 3 here, the rank of this guy is indeed equal to 3. And because the rank equal to n, which is the number of vectors, I can conclude then that these 3 guys, they are linearly independent.